Good afternoon. I hope you're still awake. We had a very exciting day. We've seen DNA, we have been seeing silica, and now we move on to ceramics. And we got a lot of buzz on just phrasing this presentation, the data storage for Yottabyte Age. And obviously the first question is, when are we there and why we need storage? I think this is why we're all here. We are concerned that a lot of data need to be stored for long term. So I'm gonna present a couple of slides. Now, what is the driver for the Yottabyte Age? I just take here the time frame 2030 till 50. It sounds like very far away, but if you look at it, we have additional data for a lot of innovations. So it's AI, it's augmented reality, virtual reality, autonomous driving, and all that. So which drives that. And we want to keep the data, and basically we have to replicate after a while, 5 to 7 years. So this makes this enormous tsunami of data possible. Now, let's look at the nature of this data. 70% of this data, or even more, are cold, depending on whom you ask. And they're rarely retrieved, already after 90 days. And sometimes you want to keep it for long periods. In the scientific field, I see a nodding, it's going to be forever. So if we look at about data from CERN. But there are also other data we care. Think about your smartphone data, your memories basically. Your family memories are on the smartphone and copied to the cloud. You don't want to lose it, and you might want to inherit it to your kids. Business data, between 20 and 30 years, depending on what products you've got. If you have like car industry, airplane industry, you want to make sure that you produced the products properly, make sure you can prove in case a liability case is coming up in 20 years that you have the data, okay? Governmental data, naturally, they are long-lived, and specifically scientific data. They are extremely long-lived because it's so expensive to create them. And finally, last one, a new kid on the blocks as we are, but is artificial intelligence generating a lot of data. And that's why I have this fun slide here. I just asked an AI on a simple question. So what is the life, the universe, and everything? Douglas Adams was phrasing this question, and put some numbers behind to get the facts. So if we think about a yottabyte, it's 10 to the 24th of bytes, okay? But it's equal to the number of stars we have in the universe. And we have about 10 billion people by 2050. And if you would love to brain scan your brain, it's about 1 zettabyte of data. So just multiply this data, and you easily end up in the yotta in xenobytes. DNA, we heard a lot about it. The genome, the human genome, has about 3.2 giga base pairs. Depending on what you calculate, you end up with a different type of bit rate or bytes. And finally, and this is where we are ending up, we store information in atoms. With 10 to the 80th, I think we have enough atoms to do that. So the first hypothesis is clarified, it should be enough. Now, another observation. Mankind was really, really clever in storing information in stone, in clay, in paper, in papyrus, in film, in tape, in hard drives, and finally in semiconductors. And a tremendous success was going on. We made data always smaller, need less space, extreme writing speeds, reading speeds, but at the same time we lost something, the durability and the resilience. And this is where we are coming in. We say, well, let's take an extreme material, ceramics, proven by age, proven by physics, that it can endure extreme timeframes on the one hand, so it's resilient and durable, but at the same time, we're going to show you along the presentation, it can be written and read fast. Now, why ceramics? It's an inert material and differs very much from like the volatility of electronic charges on SSD and magnetic polarization in a hard drive or tape. And we go back in history. There is a proof of concept going on. We tested this as societies for 5,000 years. And it's actually the same scheme. We have governmental data, like a contract, Rosetta Stone, well known. Then we have like kind of the Netflix of the Babylonian age. This is the Gilgamesh drama or epic. Actually, it's 12 plates, so it's really like serious. About 3,800 years old. And then, this I love the most. The first inscription we see as writing is a beer receipt. It was a handout of beer to workers in Mesopotamia. And that brings me to the session tomorrow. We're going to sponsor, of course, the Birds of Feathers session with some beer, and we're going to take the receipt. Now, wait a minute, we were too fast. This is an amazing piece. Did you know that this is not modern art? It was not copied out of the MoMA, but this is a sculpture found in Europe, 25,000 years old. And here comes another amazing thing. It was not inscribed by man to transform information, but there was a fingerprint on the backside, so kind of micro-information. And scientists found out that a 10 to 12-year-old girl was actually creating the sculpture. So the first artist with a new kind of material was experimenting 25,000 years in the past. And we still can identify it was a female and it was 10 to 12 years old. So a very fascinating material we are talking about. But this is not enough to get innovation going. Only in the 70s, we kind of were able to identify some very hard ceramics, which were basically brought on Earth in the meteorite. And scientists identified this and then made a series of materials being coated with this very hard ceramics to make sort of workpieces, turbines, etc., much more resistible. And other variations of that you find on photovoltaic materials. You find it even on your screen because you need some anti-reflective coating to properly see on your smartphone. It's all ceramics which is doing that. Now, how do we combine this and how do we come to this statement? It's virtually unlimited media life. Very simple. We take this very hard, very thin coating on substrates. And well, you will not believe, but ceramics sounds like brittle and very hard, but actually glass nowadays, if you make it thin enough, and the same with ceramics, they can be bent. So don't think of ceramic as something fragile. It's definitely not. But it has superior qualities, specifically if you think about thin glass. In millions of square meters, we produce this worldwide for having our displays and our smartphones covered. Now, what is the principle? Very simple, proven. I mean, we don't do a cuneiform, but we do QR codes. And why do we do QR codes? Because simply, it's the simplest way to explain it. And also, there's no license fee attached to that kind of coding. And basically, we take here ceramic nano coding, inscribe it at the moment with femtosecond lasers. We're going to see a video in a few minutes on how we do that. There's a prototype running already in Germany. But let's go first to the material, because it's about the material and the potential of ceramics for storing data. So the process is very simple. Yeah, you can have physical vapor deposition, you have a chemical agent can do that, but then you have to do something very important. You have to temper it. You have to build a unity between the coating and the substrate. And this is done by temperature. And then the writing is done very easily. You can use lasers, all sorts of lasers, but you can use also particle beams. And the guy familiar with that will probably already have a hint where the whole discussion is going. But first, let's go through the material. Well, the tempering is important, which is demonstrated here, because we did aging tests, like 300 degree for 3 days, so you can't do this properly with DNA. You probably have difficulties with other storage media. I think silica would qualify for that, definitely, and would sustain that. And you see, definitely the quality is improving if you created this sinter interface. So this is essential. But then it opens up a huge sort of variation toolkit. You have on the left hand substrates, on the right hand you have the coatings. And the left hand you will by tendency take metal oxides, which are ceramics too. They are transparent, so it's easy to read. And you have two axes. One is the melting temperature, and one is the hardness. And what you realize, these materials, most of them, are harder than steel. And then you can do and play kind of a lot of variations. For instance, we wanted to have low cost because durability is nice, but if you can't afford it, you better come up with a cheaper solution. And we are not alone with this approach. Just I read today, Intel is using glass for putting a couple of semiconductor pieces together because it has superior surface qualities. And it's low cost. But you could also do the same with flexible ceramic, alumina, or zirconium oxide. And then for coating, this is nice. Here you have really a ballpark of opportunities, sometimes even at 2,000-3,000 degrees temperature and very, very hard materials. You can even have a fancy golden coating, which I'm going to show in a second, or fluorescent. So depending on what you want to achieve in terms of longevity, you have a wide range of opportunity there. Now, let's go back to the glass. I said, well, we want to have this, and you're going to see that later, this is produced in huge quantities. And we can have it cooled down to almost 80 millikelvin. And you see before and after, it's basically the same image. The 300 degree, I explained before, this is a standard test we do. But then we thought, well, what happens if we put it on 500 degrees and put it in a sulfur dioxide atmosphere? And yes, you can see there is no change. And finally, EMP, EUV, or UV and radiation, they don't harm the material. So qualities which will be difficult with any other storage medium, especially EMP and radiation. And just give you, like, this is a small joke on cold data. They could become gold data, just in the way you take the material you want to have. And for instance, the right one is titanium nitrate. It's a nitrate again, which looks really like gold. Has specific qualities superior to that what we usually use, which is another nitrate. Now, having sort of charted the space, so there's a lot of opportunity for scientists to find even better solutions. Now let's look at the mechanism to write fast. And we basically use, actually what we use is very interesting. It's behind the screen. It's digital mirror devices for projectors. But we use it in a different way. We use femtosecond lasers to inscribe on the surface up to 2 million bits per shot, and they can be operated by 10 to 30 kilohertz. So it can be extremely fast in writing. And I have prepared a video which gives you an insight into the prototype we are running in Germany.
CeraByte is a new approach for storing data. Sheets of robust glass with a dark ceramic coating are the basis for the most durable memory media ever. Ultra-short pulses of a femtosecond laser are widened and then shaped by a digital micro-mirror device to punch permanent QR code-like patterns into the thin, dark ceramic layer. High-speed image sensors and real-time pattern recognition algorithms allow the fast readout of the data. CeraByte uses off-the-shelf components to build the writing and reading units. Our strategy of partnering with relevant industries right from the start ensures rapid scale-up. Easy integration into existing data storage infrastructure is guaranteed by the 19-inch rack size of CeraByte. Data, once written on CeraByte, stays there forever.
So we have no animations as others have. We tried to build this, and we'll have a demo version ready next year, which is up for testing with partners. Now, what did we see? We saw, well, digital mirror device. This is millions of small mirrors being able to switch fast. We have one optics through which we write and read. And on the reading side, we probably see a bit more on the software stack. It's basically a 20 megapixels camera. It's black and white, it's not color. And you have 500 frames per second. So like enormous data rate you create with that. And a lot of challenge. Sebastian's going to probably give some answers on that, on deciphering all that, because you have to resolve the data first. Having said that, we are well equipped to get to 100 megabytes per second reading speed in the first instance. Now, what makes us so different? Like anybody initially thought optical media are dead, and for a reason, because they are slow and the storage density is limited. Now let's have a look in the other concept with the digital mirror device. Obviously, here, instead of one laser, which is punching small holes in a spiral, we use the 2 million bits, and that's why we are much faster and have the potential to grow, because these digital mirror devices are improving over time. And I think the next generation is exceeding a potential speed of like 10 to 20 gigabytes per second. It's just amazing. Good. This was like the principle. Now let's look into this kind of coding and how far we can get with this. So we use the QR code because everybody understands it. It's probably not the most efficient one. And again, a look back in history. In the past, we had cuneiform codes, then alphabetic codes. We came up, the first digital device everybody of us saw was actually a CD or Blu-ray or DVD. And now we come up with the square format. Why that? Well, there are two reasons which you're going to see in a second. One is already indicated here. It's the thickness. You don't need a thick substrate like an optical disc because you have to take care for the centrifugal forces. We don't need that. And there's another reason for using a different form factor. It's simply you can stack it in like cartridges like you would find in LTO tapes. But the inside is not a tape, it's a stack of glasses. Then you have the thinness, which makes so like you can stack it on the same volume much more. And finally, well, this is not yet achieved. We have proven that we can do 100 nanometers with a laser, but not yet with the digital mirror device. So this is what we are working on. And then coming to the proof of concept, where can the whole thing go to? Well, we tested tons of different kinds of lasers, wavelengths, pulse lengths. And well, with 100 nanometers, you end up with 125 gig in one layer, which is probably 100 microns thick, on a surface of like 16-inch or 100 square centimeter. Sorry, being European, I still have to work in centimeters. And then we did an experiment which surprised all of us. What you see here is a SEM image of a particle beam. And the process size is 30 nanometers. Obviously, this can't be read with optical. So if we talk about ceramic nano memory, we'd not talk about, on the long run, in a pure optical medium. It can develop to something completely else where we leverage the semiconductor industry. Now, what are particle beams? Let's have a short exercise and see what we've got. So we said, well, obviously till 1 micron to 100 nanometers, you can work with lasers. So this is then the technical limit. Beyond that, you see really this nicely formed SEM image. And we were really surprised to have this kind of image quality. Having said that, it comes at a price because you can only read it with SAMs. And why that is, we can have a few sort of snippets out of time. So one of the founders of SAIS, Ernst Abbe, found there is a diffraction limit. And this is limiting all the optic guys since 150 years or something. And finally, Max Planck came up and said, well, we have here this quantum theory. I don't know what to do about it, and inspired a lot of researchers to do more effort. And actually, the gentleman in the middle, Einstein, he didn't win the Nobel Prize for relativity theory. He won it for the photoelectric effect. And then another gentleman came up, Louis de Broglie, and this is a fascinating character. It is said that his dissertation is 1 page. Why is it 1 page? Well, simply, if you do this equation from Einstein, photon electronic effect, and kind of model around and replace the speed of light with the speed of an electron and the mass of the photon with a mass of an electron, you end up with first of all, the first hypothesis was it's the same nature. It's a wave-particle dualism. And only a few years later, this has been proven. So he got the Nobel Prize for his dissertation, which was 1 page long. So really aspired to that kind of very effective and visionary work. And finally, you find another gentleman, Manfred von Ardenne, who finally created, on the base of this theory, was able to prove that you can kick the resolution, you can kick the diffraction limit down to the nanometer scale. And this is what actually the next slide shows. It's a kind of visionary roadmap. So we are working on the left-hand side, the colorful side, which is light and lasers. And we start off in 2025 with 300 nanometers, which brings us probably to 10 petabyte of storage density. So on the left-hand side, you see the areal density in metrics and inch format. And on the right-hand side, we thought about robotic storage and how we can stick and stack all the glasses and get to decent capacities. And this was somehow got wrong in all the response of the blocks, because they thought we will do 100 petabyte in a cartridge, while probably someone didn't read the abstract in that detail. Now, having said that, particle beams have another quality, which I come back in the next slide, but let's go for the first step, the left-hand side. What we actually achieved in the last 12 months is we took a concept which is called maskless lithography. Basically, remember, these are digital mirror devices. You put this resist on the surface, you do illumination, you do etching, and like a laborious work process, and you have small structures. We got rid of this laborious process and just took femtosecond lasers and ablated the surface. And the second achievement is we put this in a 19-inch rack. If you look at the footprint left and to the right, so this is quite a major achievement within 12 months. This is why we are so extremely fast in pushing for the market, because we use only technology which is in some form already out there. Now comes another one. We said particle beams. And just to prove that enormous speeds can be achieved, this is a company in Europe which is doing electron beam matrices. What are they used for? They are mask writers for the 28 to 5 nanometer kind of node. And at the moment, they are at decent speed of 120 gigabits per second, because they can have much higher frequency in switching the matrix of the electron beam. And as you can see in the middle, there's kind of valves, 162,000 valves, and you can switch individually the individual light beam. So this is like a blueprint for the future. Having said all that, this machine is enormously expensive. So probably we couldn't afford to do this right now, even though the storage density and speed would be astonishing, solve a lot of problems. But I again asked the AI, and we found out that we had already multi-beam electron guns in our homes. They are called color televisions. So there must be a way of getting these things cheaper. And while the AI came up with this interesting sort of frustrated astronaut looking at the Mars, it's a kind of back to the future for us. So this is what we're going to try in the next couple of years, probably with much more funding than we have today. At the moment, we have to stay with lasers and get the thing going. And now a final really bold hypothesis. If you look at this overview on like what is the market size of the various elements we have DNA sequences and synthesis. We have data storage as market sizes and with a projection to 2030. And we have semiconductor industry. And obviously an industry with then in 2030, 1 billion of revenues will have enough resources to basically help us to develop this. At that time, probably 20 years old technology, but scaled down to that what we need. So this is a wild hypothesis, and we try to prove it. So don't take it too serious. There's a lot of opportunity with DNA and other elements, but it's kind of a reflection on that. Now coming to the next one, the material. So you see already the starting of the procession to really explain how simple it is to create such high quality glasses. Just have a look at the next video. So it's basically a fusion process. It's floating down, highly optimized. And one of these machines produces about 30 million square meter per year with 3 people doing this, supporting this. So you can imagine how much data carrier on glass you can produce with one of these machines. And there's a lot of other opportunities out there. I started in the beginning. We're going to start with CeraMemory, which is like 100 microns. It's a flexible glass. But you could think of more durable things like ribbon ceramic. Yeah? Remember, we said the ceramic stuff, it can have heats of more than 2,000 degrees. This is what you can do. And finally, sometime in the 30s, you might consider the data volumes becoming too big. There is also ribbon glass, 5 microns thick, like a tape. I'm a bit skeptical if this is the right solution, because if we scale in a quadratic function on the beam side, we might not need the tape. Because the quadratic data sheets have one advantage: they have random access once they are on the drive. And this is like what we did lately. We tested one of these ceramics, coated it with titanium nitride, and we tested it from minus 273 degree to 1,200 degree. And you were able to read the material. So this was like the ambition. It's not too much serious what we're going to do. It's not like a product you would send data to space. But I find it a nice irony. Remember the golden record, which was round? We want to make it square, small, and thin. And digital, of course. Now, this is a wild fantasy and vision how data carriers could evolve around ceramics. But to build this and make it reality, we need partners. We need to build an ecosystem, because no one, no company, nor individual can have this built in the few years we are left for getting to the Yottabyte age. And so this is what we actually built. So happy to invite you guys and your companies to participate in demo systems in 2024. It's going to be a modest 1 petabyte per rack system, 100 megabyte speed, and 90 seconds to the first byte. As you can see, this evolves over time significantly towards the end of the decade. So a lot of effort and joint development is required to get this up to speed and get the high storage densities. So it's not an easy thing, but I think we're on a good way, because you use proven technology and put them in a different, in a new way. We have been asking for feedback for several partners from the archiving space, platform space, we call it, or cloud providers, or the sourcing. You find some prominent names in there. We got very positive feedback, so there was no reason to believe that this can't be done if enough people are collaborating and getting this to life. And this is basically the call for action to you guys. We want to have creating a cold data storage ecosystem, which is actually not one supplier left as we have it, for instance, with tape, but rather have a vivid ecosystem with several partners in each of the value chain steps to make this really large and grow with us. So a similar, like Microsoft was asking for that. We basically in the same league, and we have to talk with the gentlemen in Microsoft because they see a lot of similarities in the material and the femtosecond lasers we use. So happy to take up the ball there. And yeah, what we're going to do is you can go on our website. There is a link where you see the video with a prototype. Reach out to us, and we're going to try to make something happen in 2024 on several levels. It might be whole systems. It might be tests of software and interfaces. I'm going to disclose tomorrow in a session around 3 a bit more about that, how this comes to life for the laser bit. Yeah, and finally, this is a big endeavor, and kind of it's interesting that our team reflects 2 generations, because we don't see this as like a project ending in 2030. It should be going on in the 40s and 50s, and we need young, ambitious people to help us to get this done. Any questions? So the question was if it's data center grade or is it to be placed somewhere. I think it's both in a sense. Yeah, you can think of use cases where you don't need hundreds of petabytes. It might be archives and institutions who want to take care that the data are on their premise, right? And for that case, you don't need specific environment. Yeah, so you have the data carrier which lasts quite a long time in almost impossible environments. And you have, of course, lasers which have to have some ramifications. So you should probably not operate them at 60, 70 degrees. So there is some requirements on that. And on the hyperscaler side and data center side for corporates, there you have a bit more controlled environment, but also sometimes very harsh environment. Nowadays, data centers become hotter and hotter, just not wasting so much energy for cooling. And according to some conversations, it might be a massive swing in temperatures, 5 to 50 degrees centigrade, which is crazy, with an enormous humidity along. So this is going to be challenging also for us. Specifically, humidity and optics is not going along well. Let's put it this way. I hope this answers the question.
In terms of cost-effective commercial availability, and you give it to the guidelines, I asked because there was a email discussion in section of the bulk this morning. I've got my ideas about that. Could you share
So the question was about the cost effectiveness. Well, obviously, what we do right now is not cost effective, right? The components are expensive, and if you have small batches of glass shipped to you, it's very expensive, but it's the scalability of the system. So I think commercially decent and available systems can be provided by 26, 27. And while the target pricing for the medium, because it can be produced in large quantities. So let's assume we go into 500 exabyte, 1 zettabyte in 28, 2030. We estimate the media price being below $1 per terabyte.
So electrical units There is a limit of how many times you can read without damaging the substrate.
So the question was if there is a limitation on reading when we use electron beams. And we think it's possible because the material, we actually have the other problem with electron beam at the moment. You have to have very specific coatings to have an interaction between an electron beam and the surface. Yeah, so like that you can avoid the etching process. And so you have the other problem. It's difficult to write at the moment, but there are coatings, and we know papers. We didn't try it ourselves, but we know papers where this has been done. And then you just get down the resolution and the power for the scanning beam. I mean, think of it: electron beams, scanning electron microscopes are used for biological probes, and they are fine with that. So I wouldn't worry on that side. I would rather worry on the writing side at the moment. But happy to test this on CERN.
The question was the effect of the DME with respect to the electron beams of your thermostat. Again, it's recording that I guess that look after the areas over there, the DME.
Sorry, could you rephrase?
Similar question, but mainly on the writing side.
Yeah.
The DME, the coatings on your mirrors, the same.
Yeah, we have to be careful on that. For instance, it's very difficult. So the question was if the DMD is actually having problems if you have a strong radiation. So far, we found out for the process and the thin layers we have, we need only 0.1 nanojoule per bit. It's a very low fluence, much lower than for like inscribing something into silica. So that's why basically we think we have just found a sweet spot area where this is exactly working. Applying this with current technology, with current mirrors, macro mirrors, to a silica plate, for instance, wouldn't be possible because the energy levels are like 100 times higher due to the nature that our material is absorbent, silica is not. So there is a sweet spot where it's working, but I wouldn't go so far that this can be generalized. But there's ways of getting the performance of these mirrors much more improved. They take at the moment 10% of the energy, but you can think of other methods coating this material in a way that the absorption is lower.
It sounds like you're not very worried about delamination of the coating.
Yeah. Yeah, only if you do this tempering step. So the question was about delamination. Does delamination happen? We only realize delamination already at the way when you start to do the writing, when you did not properly do the tempering before. So this is the essential part. It's like burning in the surface and make it a sinter interface. Then it works perfectly, and this is actually why this is working. Yeah.
When you put the data into fresh ceramic, what happens to all the treating that is afflicted away? I think that's like 50% of the total.
Yeah, in average it's 50%, but basically, sorry, or what happens to the ablated material? So first of all, it's very fascinating if you see microscopic fast track videos of the ablation. It looks like a mini atomic bomb sorry for that, but it really looks like a mushroom. And it's only 150 microns high. So what we had no problem with the optics. We made sure we had like at least 1 centimeters away. And then it's a suction system. You get rid of that material. And yeah, think of it. It's 10 nanometers of thickness. So it's 100 atom layers, which we ablate and calculate the surface depending on the structure size. The number of atoms you've got is limited. And the other thing is a good part is nitrogen. Yeah, so this disperses into air. This can be handled.
A similar topic, when you have ablation, now you have explosion of the particle into the air or above the surface. Do you have ablation occurring and with that affecting your resolution?
Not really. Yeah. So the question was, does we have an effect when we get this sort of ablation plasma firing up? We have discovered, because we write very fast, so we write in a matrix. So and then you move on, and we leave a bit of interstitial space between that. And the time how this is developing, this is also in a very short time frame. Usually you have a lot of blinding light from the plasma, which takes about 20 nanoseconds. And this is a nice thing also to mention, we can't read after that blinding spot immediately. And so we don't see any problems of firing one thing after the other. But it's only, you have relative high speeds. If you want to have high data rates, so I'm getting some sign, we are running out of time. We have 5 minutes left, but I hope this answers a bit.
So the data would be encoded directly on the surface of the material? Are you like laminate another layer of protecting just writing that piece of media?
Actually, the question was if we afterwards laminate the material. Out of practical reasons, we think this is not required, because remember, the characteristic of the ceramics is it's harder than steel. So you don't have a problem with that one. So if you do a proper suction and you don't have like particles sort of distributing on that, this is not a problem.
So you're not worried about the 12-year-old girl looking for fingerprints?
Well, we have a restriction on 12-year-olds in data center, I think. But even that is this thought of, I mean, the Microsoft gentleman, Sasha, was also mentioning this. There is ways of cleaning the surface. So if it's organic material, you can clean it with a laser. So even if there is dust and something like that, you can manage this.
Also, one thing is enclosed with kind of cartridge, like LCO2. So I mean, they're not actually to get to the FDD.
Exactly. So the question was like, the protection of the cartridge obviously helps a lot, and this is absolutely necessary also for handling reasons. We want to make sure we can access fast, and in this sense are faster than tape, because once the cartridge with the stack is delivered, you can have random access. So this is the idea behind that. And you have then a sort of protection. It's not completely 100% sealed, but you can manage this. And actually tomorrow we're going to show a bit more about in the session on how the robotic storage works. It's a bulky machine now, but we hope to make it small and viable for any data center use in the near future. So as we speak, we just merged this writing component with the robotic storage, and tomorrow I'm going to show you a video on that. I have to apologize, it's still very bulky, but I think we wanted to demonstrate that this can be implemented in a very short time frame with standard components again.
Assuming the femtosecond laser might be one of the more expensive components in your system, is it your hope that that will be democratized in time, or is it still being the expensive part?
So the question is about like basically the cost of the femtosecond lasers. We all know that femtosecond lasers is probably not the cheapest laser we can get. Okay, so there are two answers to that. First is on the short term, we think the femtosecond lasers we've got are required because there is no semiconductor laser yet which can do that. We have been in talks with one of the larger electronics companies who do this to semiconductor and lasers for LiDAR, and they seem to be a good guess for a system which is more cost effective. And the other thing is, due to the fact that we don't need so much energy for ablating the 2 million bits, in theory we can run like 10 heads on one laser. I mean, it's technically challenging to do a distribution system of this, but this is probably the way forward of the shortage. Oh, I see we have to end. Of the shortage of lasers. This is a serious problem, but probably together as an industry, we could solve that, because there are many examples in the past, like if the volumes were not large enough, but if the interest is growing, then you're going to get to the point where you have sufficient lasers available. Any other questions left? I mean, I don't know whether we are kicked out of the room.
You've got about 5 minutes left.
Yeah, we have 5 minutes. Okay.
But you can also give up.
No. It's no, never give up.
Did you ever follow any of the work from the, I think it was the 100-year archive project at MIT? Because they were looking at issues of having to migrate to new types of storage and what file formats are going to persist for a very long time. There may be some lessons there that are useful. Although right now you're in the technology development stage.
Okay. Would be interesting to reach out. So that the question, well, it wasn't a question, it's like the comment that MIT is working on sim.
I think it was called a 100-year archive project.
Okay.
I don't even know if it's going anymore.
So we have to. Well, probably it goes. Was it like it goes for 100 years, or I don't know. But we gotta find out. Yeah. So there is a company called DOTS, which have a similar concept, I would say, in the sense that they use metal alloys on the surface of an organic material, organic substrate. And definitely it's an interesting concept. We are in exchange with them on ways of making our technology, which is, I think, in terms of writing much faster. We try to find out if we could work with their material. I mean, this is kind of a different concept. It's a phase change, but I find it very interesting as a concept, because it leads into what I said. Well, CeraTape could be something, and there are some similarities we have to explore.
Sorry, his comment about the MIT thing triggered a thought, a question. Do you know who has some of the oldest digital data? Does IBM have data that they collected 50 years ago when they were creeping on us? Right? Because all the current internet companies, they weren't around 50 years ago. So
Yeah, sure.
do you know who was the people? Do people have digital data companies? Have digital data that is?
That's very, very old. So the question was whether I know other companies who are having these old punch cards as a data carrier. I think a good resource for that might be research institutions which are around for very long, rather than IBM, because they are busy with other things at the moment. So I guess there is a lot of. It could be with CERN, which was founded in the 50s, could be other programs in the science space where you have digital record that old, which is copied every 5 years to a new tape or something.
I just think it would make a good story to say that people are already doing this.
Yeah, sure. So we have. Thank you for the advice. We have to find these organizations which have this problem of ever copying since 50 years or more. It might have started in 50 when the first computers came to life.
At least one such organization is here. It's Los Alamos.
Yep, absolutely.
And I guess a lot of it depends upon your precise definition of the word.
And that's why I think 50 years should be doable.
50 is absolutely doable. I mean, think of it. The optical disc was invented 40 years ago, so there must be.
For a while, I worked at HDST, which had bought part of IBM that invented the disk drive. We had a RAM sitting in the lobby, which was 3 tons and held 10 megabytes, and had 40 platters.
Wow.
Now, whether you can recover data off that, I don't know. And there was the other story that NASA had tapes from the 60s for the manned spaceflight program. They had no tape drives to read them. They didn't remember what the format of the data was. On and on and on. So I don't know how successful they were.
But there's a need for the very old data, definitely, and especially around the space program, which was so expensive for society. There are rumors that some of the most important videotapes were overwritten many years back, and it's really sad because they were the highest quality at the time. They were residing, I think, in Australia, and they had some. Well, it was not digital; it was an analog tape, but it happens that these things are overwritten. Yeah. Yeah, yeah.
Even worse, they lost some of the original episodes of Doctor Who. Because they were always written over, and once in a while you find a new copy that's around somewhere, but they're missing episodes. That, you know.
That's really.
But that was film, so not digital.
Yeah.
Right? Screwed it out. Started as a USB drive. What the hell did you do?
So, make your speaker.
Thank you.